Hello, and welcome to another edition of Mr. Chappell's Chemistry Screencasts. Today we're going to talk about using the Bohr equation. What you'll learn in this screencast is how to calculate the wavelength of light emitted from a hydrogen atom using the Bohr equation. Now there are a couple of things you're going to need. You're going to need a calculator, of course, and you're going to need the Bohr equation. Let's go ahead and get started. Okay, here's a typical problem. We've got an electron going from n equals 6 to the n equal 2 energy level of a hydrogen atom, and we're being asked to calculate the wavelength in nanometers. And the first thing you want to do is go ahead and write down the Bohr equation. And the Bohr equation looks something or exactly like this. And let's go ahead and plug in the numbers. The first number is the Rydberg constant, and that is a constant, so you'll always have access to that during a quiz or a test. And I happen to know it off the top of my head because, well, I don't have a life. And so it's going to be 2.18 times 10 to the power negative 18 joules times the quantity 1 over the initial energy level, which is going to be 6 squared, minus 1 over the final energy level squared, which is going to be 2 squared. Now we go ahead and break out our calculator, and if we do it right, what we should get for an answer is negative 4.84 times 10 to the power of negative 19 joules. And that looks about right. And it's a negative value because, well, we're looking at this from the electron's perspective, and it's lost energy since it's going from a high energy level to a low energy level. Okay, the next order of business is to figure out what wavelength is associated with that energy. And the equation we want to use is wavelength is equal to Planck's constant times the speed of light divided by the energy change that we got from the Bohr equation. And since this is the energy being released, we need to remember to take off that negative sign. And the Planck's constant H is 6.6 times 10 to the power of negative 34, and that's joules seconds, times the speed of light, and the speed of light is 3.00 times 10 to the power of 8, and that's in meters per second. And lastly, the downstairs number is going to be our energy. And we need to remember to remove that negative sign, 4.84 times 10 to the power of negative 19, and that's in joules. And let's just make sure that the units cancel. Joules cancel here, seconds cancel here, and the only unit left standing is meters. And that is a unit of length. That's kind of what we expect for a wavelength. And so the answer that you should get is 4.09 times 10 to the power of negative 7 meters. Now we're going to need to take that value and convert it into nanometers. So let's just go ahead and put that measurement over 1. And if I'm not mistaken, for every 1 meter, we're going to get 10 to the power of 9, that's a billion, nanometers. And the meter unit cancels. And this is going to be our final answer. 409 nanometers. And that's our final answer, and that looks just about right. And this concludes this lesson. Okay, it's joke time once again. Hey, did you know that when a clock gets hungry, it goes back 4 seconds?